Welcome to second lecture of Tribology course. Title of this lecture is Interdisciplinary Approach and Economic Benefits. In previous lecture, we started with one example, contact between two surfaces, or more particularly contact between two rough surfaces. We say that there is a surface 1, surface 2, and there is a possibility of relative speed when we are applying some force on surface 1. Due to this force, this component surface 1 will be pushed against the component 2 or surface 2. In that situation, there are number of possible situations. One is that there is a possibility of elastic bending of asperities. Second possibility is that breakage of surface asperities, and third possibility is that plastic deformation of soft surface. What is the meaning of that? If one surface is much softer compared to other surface, in that case harder surface will plow the soft surface, will cut number of grooves in soft surface. We know to avoid failure, to enhance the life of component, what we require only elastic deformation. We cannot tolerate too much breakage of asperities. We cannot tolerate plastic deformation of other surface. This will reduce the life of component. Therefore, our emphasis will be more and more elastic deformation or no deformation at all between these two surfaces. However, there is a problem. When the component is new, there will be irregular surface. That is why there will be some breakages of asperities, which is tolerable. That is why we showed yesterday previous lecture this bathtub curve. Bathtub curve clearly indicates initially wear out will be more or rate of wear will be more. It will reach to a steady state condition, and that steady state condition is going to decide what is the useful life of the component. Once that useful life of the component is over, again wear rate will enhance, will increase, and that will increase the clearance between component, will increase the noise between component, will increase the vibration between components, and we need to change, replace that component. So, based on the tribological knowledge, we can avoid excessive wear, we can minimize excessive wear and enhance the life. Number of possible combination or number of possibilities which we can think to enhance the life, or something like we can use lubricant to avoid the breakages of asperities, but lubrication itself is a subjective term, with the thin film lubrication, thick film lubrication, or just partial lubrication. To quantify all this, what we can do, we can define a parameter what we call a plasticity index. Here it is either psi is equal to 0.6, in bracket we have E divided by H. Here E appears to be Young's modulus, and what we are saying here, this Young's modulus is a composite Young modulus or effective Young's modulus. It accounts both the surfaces. It accounts Young's modulus of both the surface as well as Poisson ratio of the surfaces. Additional term is the square root of sigma divided by beta. Here the sigma is the roughness, surface roughness of the component, while beta is the spacing between the two peaks at which we take at any time. To continue with this, we can say if plasticity index is very low value, that means it is going to give us more and more elastic deformation or lesser breakages of asperities. Service life will be much better. So, we need to keep this plasticity index to minimum. How can we do that? First, if surface roughness value is high, the typical figure is shown over here. You can see the surface roughness, peaks and valleys, certain peaks are coming out, that is harmful for the machine component. If this surface roughness is higher, naturally plasticity index will be high value, and because of the high value of plasticity index, there will be some sort of deformation on the surface that will lead to reduction in the service life. Then another one is Young's modulus. It's interesting to note that we are emphasizing on low Young's modulus. Low Young's modulus will reduce the plasticity index. In general mechanical engineering and other streams, generally we prefer high Young's modulus, but from topological application point of view, we prefer low Young's modulus. That's interesting thing. In addition, we have another parameter, that's a hardness. Higher hardness will always be preferable. If you want lesser wear rate, high hardness will be preferable, and high hardness also reduces the plasticity index. That means, if we are able to keep low plasticity index either by means of Young's modulus or hardness or surface roughness or any combination of this, that will be good option for us or to increase the life of component. One of the easiest method to that to achieve low plasticity index is use a third substance between two substances. Let us take this example. Here we are showing the force is pushing a one component. I am assuming this is a trolley, and there is another component over here, maybe I am assuming there is a ground. We are trying to push trolley on this ground, and there is a carpet in between. If this carpet has some fibers, we know carpet fibers will be elastically deformed if there is a force by trolley, and elastic deformation of these fibers will not take too much force. They will be easily bent. As they are easily bendable, friction force on this will be much lesser, and wear will be almost negligible, and that is preferable for us. Now, coming to the mathematical term, we say generally we find a stress, linear stress, or we say uniaxial stress. That stress can be figured out or can be calculated, can be estimated by using force divided by area expression. Here area in this case is apparent area, which is generally used in mechanical engineering. But when we talk about the tribological components, we need to take only fraction of this area. We know very well whole area cannot be in intimate contact due to the asperities, and because of the asperities, effective area or real area will be much lesser. 99%, this area is lesser than 16% of total area. As a lesser than 16%, so I can say effective stress on the machine component will be almost 6 times compared to what we calculate with ordinary formula. There is a possibility of 6 times stress, or another one possibility is that if there is a high stress is equivalent to the elastic limit, naturally the component of asperities will bend and will allow other asperities to come into picture. Or in other words, if the load is more and more asperities will come into contact, reduce the stress back to the stress elastic limit stress. That is a preferable, and maximum in that case if the whole area, whole real area is equivalent to apparent area, then in the situation we can say that can tolerate that much maximum force. Now, I can add one more sentence in that. You say the why we prefer elastic deformation of the asperities. Reason being that due to irregular surfaces or irregular surface where the peaks and valleys are there, if the peaks are bending easily and then they are getting filled one way or another way to the other irregular asperities, then it will provide us very smooth surface, it will provide us plane surface with much lesser irregularities, and that is what we really require from topological point of view. We can say that will provide us smooth ride. However, there is a limitation. We know from fatigue point of view, if any component is elastically deformed again and again and again and again, there will be cyclic loading, it will experience cyclic loading, it will experience fatigue. And if this fatigue having some endurance strength, stress is beyond or more than that stress, the component will be having limited life. We know other than iron or ferrous material, not a single component has any endurance strength. That will be continuously decreasing. A component will tolerate or can tolerate much lesser stress on high number of cycles. So, almost all the components other than iron will have limiting life. If I am using any lubricant, that also will have a limiting life. That is why we need to replace lubricant frequently or depend on duration, maybe say after 10^6 cycle, maybe 10^10 cycle, for which it was designed. Now, whole this slide was related to the surface roughness, hardness and Young's modulus. It has been experienced the surface roughness plays a major role compared to other properties, Young's modulus and hardness. Reason being, surface roughness will continuously change. Initially, maybe surface roughness is a 1 value. After operating some operating hours, the surface roughness value will change. It may be better side, may be worse side. If we are able to achieve better surface roughness, that means component is coming to the steady state. It will survive for a longer duration. But if surface roughness is enhanced or increased, the value of surface roughness is increased, then in that case component is going towards a failure. It is not reached to the steady state condition, but it will be subject to the frequent failure. So, there is a need to give couple of slides or explore couple of slides on the surface roughness. That is why I am projecting this slide. We say the surface roughness, and a meaning of the surface roughness is the vertical deviation from a nominal surface, nominal line. If there are larger magnitude, deviation is a larger, naturally surface will be rougher. And that is why this line shows there is a nominal line is passing through almost the center, and these are the peaks and valleys. This magnitude, this amplitude shows the surface roughness. Larger the amplitude, larger will be the roughness. To evaluate this surface roughness, often use a measuring equipment. And when we try to measure the surface roughness, we account 3 lengths. One is called a traversing length, other is evaluating length, and third one is a sampling length. Reason being why we are choosing 3 length is that we do not want to account start and stop of measuring equipment. There is a possibility that at the start some jump phenomena happens, and similarly the exit some jump phenomena happens. So, we want to avoid first and last portion. We want to account only 5 portion remaining, and the sampling length is, I am assuming there is a 1 portion. We know the surface roughness is statistical. We cannot find a single value. So, what we do in that case, we try to average these 5 sample lengths, and whatever the data comes, that will be mean surface roughness. So, there will be some mean value of surface roughness as well as a standard deviation. Have more number of sampling lengths, it will give better result, but it will consume more time, and that is why as per the standards they have come to the final figure of the 5 sampling length that gives a reasonably good results to us. That is why we are choosing this mode. Now, from tribological point of view, as I earlier mentioned, we will be choosing, we will be preferring low surface roughness value surface compared to the high surface roughness. So, in other words, I will be choosing or I will be preferring left hand side this image compared to the right hand side this image. There is a possibility maybe the average surface roughness of these two comes to the same, because there is a valley over here, there is a peak over here. If I sum up these two, I will may get the same results, but I will be preferring this portion compared to this portion because of the lesser surface roughness in this side or lesser value of the peak, but this is again at the start only. If there is a possibility of fracture of this sharp peak at the start itself, then there is no problem, we can choose this surface roughness and this surface also. However, to implement this kind of approach, we generally use running in time between the components. We know when we buy a new car or new automobile, it has been instructed, or generally people instruct or company instruct us to drive that vehicle at the lower speed, so that all running in or the bedding in time is over at the lower speed, it does not cause a catastrophic failure. After driving low speed for some time, we change the oil. That means, all the large size asperities are broken or tear away from the surface, they get they get mixed with the oil, and we replace that oil and we get good surface for the longer life. After that, we can speed up vehicle, we can drive vehicle at the higher speed. Now, there are number of surface roughness parameter, what we call the peak amplitude related parameters also. Most commonly used surface roughness parameter are average surface roughness, where we take peaks and valleys and sum up and take average value of that. Our one is the root mean square surface roughness. We again take peak and valley, we square it, we average it, and then we take a square root of that. In tribology, we generally prefer RQ value or RA value, or we prefer root mean square roughness compared to the average surface roughness. Reason behind this is that average surface roughness does not signify completeness of the peak and valleys. We say that we want to penalize peaks slightly more compared to low peaks, or we say the high peaks should be penalized more than low peak values. If I count only the average surface roughness, then there is equal weightage given to the low value low peaks and high peaks, while when it is we are taking the root mean square roughness or RQ value, in that case a more penalty is paid by high value peaks. And as I mentioned earlier, the roughness changes with operating time. So, whenever we are designing component, we need to design component according to the time. Is a short life component, is a long life component. If I have to design component only for the 10 hours, naturally I will keep bedding in time at the own industry. I will not give the component to the customer at all. But if I know the life of the component is 15 years, 20 years, then maybe the bedding in time can be given to the customer, let them have feel that they are buying a fresh component, they are buying a new component, and new component will have always asperities and valleys, and let him judge his component as per his wish. To quantify surface roughness, as I mentioned, we use equipment, and what the equipment generally does, it breaks a whole surface in number of digits or number of points. And like in this figure, we are showing there is one surface and it has been divided maybe 60 divisions, and then this 60 division we try to find out what is a peak value. For simplicity, it is shown only sinusoidal profile, but in actual case it may be any random surface. What we do, we divide component, whatever the analog signal we get, we divide in number of parts, and based on that division we evaluate what is the Z value, what is the peak value, what is the amplitude of surface roughness at that point. We sum up. To avoid getting a zero value of surface roughness, we take absolute values. As in this case, we are taking absolute Z1, absolute Z2. Similarly, when we take absolute Z11, Z12, then we will be able to get really good average surface roughness. It is a sum up, and the N is a total number of points which we have accounted. As earlier mentioned, there is another surface roughness parameter which is preferred in tribology division or tribological application is RQ value. An interesting thing is that RQ value will be always higher than RA value. That is good for application point of view. We are taking more conservative approach, and as I mentioned earlier that we penalize peaks. So, if Z is lower, maybe say 1 unit, it is going to get only 1 unit, but if Z is 2 unit, result is going to be 4 units. So, the more penalty is paid. If Z is 3 units, Z square will turn out to be 9 units. So, much higher penalty on that. That is the reason why RQ value is preferred or RA value. It gives much more meaningful result from topological application point of view. Now, we have studied RA and RQ values. Let us say which surface will be preferred and why we are choosing RQ. As I mentioned earlier, there is a penalty, more penalty on the high peaks, particularly in RQ value. Let us see that this example. There is a one surface, there is another surface. Now, I am trying to find out RA value and RQ value for this surface as well as this surface. What I find RA value is a 0.25 microns in this example. Similarly, RA value 0.25 in this example. However, this has a number of values. Now, coming to the RQ value, in this case RQ value is 0.58, while in this case RQ value is 0.37. So, what we are saying, whatever we were planning to give more penalty to high peak value, that is being imposed on this. So, we can say based on RQ, high RQ value, this bearing surface or this surface is bad surface or this surface is good surface, and again these are only comparative terms, they are not absolute terms. I am saying that this surface or this portion, right hand side portion is better than left hand side portion. We are not saying an absolute this is the best, much better values can be obtained, right. So, I can conclude on based on this diagram is based on lower value of RQ, second surface right hand side surface will perform better than first surface. However, there is another clue about this surface. You can see there are valleys. Many times we say these valleys are helpful to us as a storage of lubricant. If I supply lubricant, that will get dumped in these valleys. So, it will provide me a storage space. I do not have to keep larger clearance between two surfaces to keep lubricant firm. If the lubricant can be stored in this valleys, it is more like I am getting a natural resource in a surface itself. So, that will give me a good results. In addition, this kind of surface is preferred from wear point of view. We when one surface wears out other against the other surface, there will be some generation of particles, and if these particles come between two surfaces, they will reduce area of contact, real area of contact. That is a harmful. Again, that reduction in area of contact will increase the stress value, and there is a possibility of jamming two components or high wear rate. So, in that case, particularly these valleys will act as a dustbin. If the particle debris is generated, it will get dumped in the surface. It will not be between two surfaces. It will not kept a longer time in between two surfaces. So, that is a beneficial for us. So, in short, we can say this right hand side surface performs better from lubricant storage point of view to remove debris from this contacting surface. From these two point of view is very good results. It is going to give us good results. That is why many times we use the word as a segmented surface. This surface is more like a segmented surface, and to some extent people can appreciate this surface from energy point of view, from heat dissipation point of view. In this case, heat will be there if only the straight surface is there, plane surface is there, effective area of heat dissipation will be lesser compared to heat dissipation area in this surface or available on this surface. So, this kind of segmented surfaces, this kind of punch surfaces or nodulate surfaces will be preferred over irregular surface. To add some more value, to find whether the solid mechanics should be used, fluid mechanics should be used, material science should be used, or chemistry should be used, or a combination of all four subjects should be used simultaneously, we can define one parameter that is known as a dimensionless film thickness parameter. It is a ratio. It is a ratio between the separation between the two surfaces over what is the composite surface roughness. So, here RMS value of surface A, RMS value of surface B are accounted. So, if RMS value of any one surface is higher, then overall this thickness ratio or is a dimensionless film parameter or lambda will be lesser. To increase this lambda value, we need to increase separation between two surfaces. That means, if we are providing the lubricant layer between two surfaces, or we are providing some soft material between two surfaces, or some powdery material between two surfaces, that is going to increase this capital lambda value. If the capital lambda value is higher, then operating mechanism will be different and overall result may be in favor of the site. So, we generally divide in 4 domain the complete lubrication mechanism in a 4 domain. We say that the lubricant is negligible. That means, there is hardly any film thickness between two surfaces. In that case, capital lambda will be lesser than 1. That means, surface roughness is a higher value compared to film thickness. However, if we are providing some lubricant, partial lubrication, then this value will turn out to be lesser than 3, but greater than 1. If we are providing thick film lubrication, it will be lambda will be greater than 5. So, what we can say, in that case, this is a hydrodynamic lubrication, there will not be any contact, and life of the interacting surfaces, contacting surfaces will be infinity. There will not be any wear, there will be only friction, and we are saying that because of wear, component has a restricted life. However, there is a possibility intermediate stage where the lambda is greater than 3, but lesser than 5. In this view particularly, there will not be any asperitic contact, but there will be elastic deformation of asperities. While in earlier case, hydrodynamic case, there was no deformation of surface at all, no deformation of asperities also. While in this case, deformation of surface is accounted, which is a more natural phenomena. We have so many bond joints in our body, and almost all the joints work on elastohydrolytic lubrication mechanism. Even the gears, bearings, cam and follower, they work on elastohydrolytic lubrication mechanism. That is a most economic tribopair for us. To give more insight about this, we can plot one Sommerfeld number, what we call as where the viscosity of the lubricant is accounted, relative speed between two components is accounted, and pressurized apparent pressure which is applied on the surface is accounted. We are using the word here apparent pressure because it is not real pressure may be greater than this apparent pressure. In this case, we are directly using the word force divided by area, which is apparent pressure. In real case, it will be force divided by real area, and the pressure may be 6 times or 7 times more than apparent pressure. Now, when we plot coefficient of friction with this Sommerfeld number, what we find, when the Sommerfeld number is low, coefficient of friction is high, and that is signifies a boundary lubrication. Boundary lubrication coefficient of friction is relatively high. However, there is a lot of discussion keep going on this survey, whether they really initially coefficient of friction may be that low. That is difficult to achieve, because we cannot achieve 0 speed whenever there is a 0 speed or 0 viscosity or infinite pressure, we cannot get any result. So, that is why there is a always possibility to leave a slight gap between this and y axis, or the coefficient of friction axis. Now, this figure shows as a apparent as a Sommerfeld number is increasing, which may increase due to the apparent viscosity, maybe speed or reduction in the pressure, any one parameter or a combination of all 3 parameters. The coefficient of friction is going to decrease. It reaches to the bottom, the minimum value, and after that again increases. So, we are always targeting, if we want to design a tribopair, if we want to design a machine component, we should prefer this lower portion, where the coefficient of friction is a minimum. That should be our target, and if it is not achievable, then we may negotiate with the hydrodynamic lubrication or to some extent mixed lubrication mechanism, depend on the operating condition, depend on the device for which we are working. Now, if I see the wear behavior, ideally there should not be any wear for the hydrodynamic lubrication and mixed this what we said, this line as a last order lubrication, but in reality it will always be there due to start, during stop or some transient force operation, there will be some wear. So, that is why the minimum wear is shown in the case of a hydrodynamic lubrication, that is a green color line over here. Now, we are using two parameters here, one is a load. If the load is increasing, slowly hydrodynamic lubrication will turn out a mixed lubrication to the boundary lubrication, and if the temperature is increasing, which will reduce the viscosity, same thing again will happen. Indirectly, it is going to increase the load. Now, if I try to relate this parameter over here, what we are saying, if the load is increasing, Sommerfeld number is decreasing. That means, if the some component was under hydrodynamic lubrication, slowly is moving towards the left hand side, it will see the red color portion, and then if still high load is applied or temperature increased, then it will turn out to be boundary lubrication mechanism. So, every hydrodynamic lubrication mechanism, if subjected to higher load or severe load, it will turn out to be mixed lubrication mechanism or it will turn out to be boundary lubrication mechanism. If I for the same load condition and a different area condition, if I assume, we find always the wear rate in boundary lubrication mechanism is much higher compared to hydrodynamic and mixed lubrication mechanism. So, we should avoid as far as possible boundary lubrication mechanism. We should provide some lubricant one way or another way. I am not saying that it has to be a liquid lubricant, it can be any lubricant, it can be hydrodynamic lubricant, it can be gases, it can be solid lubricant, which can be utilized to lubricate to surface, which we will be detailing when we treat a friction or wear topic of this course. Now, we require really a true interdisciplinary approach to find out the real good results. If I treat or deal with only boundary lubrication mechanism, I require material science, I require solid mechanics, and I require chemistry. Chemistry is required to find chemical reaction between the surface and contacting surface or contacting lubricant layer. Under a mixed lubrication condition, we need to have all four disciplines. We cannot avoid any single discipline. We require material science, we require fluid mechanics, we require solid mechanics, we require chemistry. All four disciplines are essential to find out true mixed lubrication results. Under hydrodynamic lubrication, which is one of the simplest and most extensively used in a number of textbooks and number of lectures, is fluid mechanics. It is one of the simplest one. And under elastomeric lubrication mechanism, we need to use solid as well as fluid mechanics. We may not use in this case material science to a great extent, only the material properties are required, which generally are covered in solid mechanics, and we require fluid properties and fluid effect of a loading condition on the fluids. So, that can be utilized in a fluid mechanics. So, for elastohydrodynamic lubrication, we require both solid and fluid mechanics. For hydrodynamic, which is one of the very simplest one, is it requires only fluid mechanics. Well, one of the difficult, or say one of the most difficult, is mixed lubrication mechanism, where we require all four disciplines, where we require a number of iterations to get real good solution. Now, there are some other points also. We say that we are not covered hydrostatic, aerostatic and aerodynamic in this case. So, that question is obvious in this case. We are assuming that the hydrostatic is more like hydrodynamic, only the pumping source is getting changed. In hydrodynamic case, pumping source is self-acting, is a relative speed and a combination with a load, while in a hydrostatic it is a extra pressure or external pressure which is fed between two surfaces to levitate one surface with relation to the other surface. Same thing with aerostatic. In case of aerostatic, we are putting gas. This gas can be anything, it can be nitrogen, it can be any neutral gas, it can be air also, which is not going to corrode the surface. That is only our aim. Otherwise, any gas can be utilized. So, that way we can say aerodynamic bearing will be the cheapest, because the sources are naturally available. I can directly pump or send pressurized air between two surfaces, but there is a difficulty. In this case, particularly viscosity of air is much lower than any fluid viscosity. So, we need to have much smoother surface for aerodynamic bearing, which is very difficult to achieve. That is why it requires sophisticated manufacturing processes to find out, to develop aerodynamic mechanism or aerostatic mechanism. Another interesting fact which I want to highlight is that maybe sometime you keep using only aerodynamic lubrication mechanism, assuming two surfaces are always separated, and we are accounting at the initial level, at the start level and the end level. We are pumping liquid, we are levitating two surfaces or one surface related to other surface, and we are always trying to keep mechanism or contact pair under hydrodynamic lubrication, but it is not a general case. If there are some dirt particle passing in liquid, they can occupy the space between surfaces, and then they can reduce particles film thickness, or it can increase effectively the surface roughness. So, every aerodynamic mechanism can be shifted to the mixed lubrication after operating condition. So, we need to, in real sense, we need to account all four disciplines whenever we want to attack any tribological problem or any tribology problem. There are a number of benefits which we can gain when we apply tribological knowledge. Maybe say if we learn all four disciplines and coupling between all four disciplines, we can utilize those equations, that knowledge, to increase service life, reduce friction losses, increase wear life, or reduce material wastage which has been done either in a lubricant form or in solid form, that can be saved to a greater value. This was pointed out in 1966 by Jost report, or it was pointed in Jost report by Peter Jost and his company, his committee members. He pointed out that we can save, UK government can save 515 million pounds per year just by implementing tribology knowledge in UK industries, to avoid breakages between the components, to reduce downtime, to reduce inventory cost. He could calculate 515 million in 1966. We know number of machines have increased now drastically compared to 1966. There are many new machines have come up, much more sophisticated machine where the earlier tribology was not required, but now it is required. So, if you count those many applications, we can save a lot of money, we can save a lot of money for our nation, and that can be used for some other good purposes compared to just getting wasted in tribological components. It has been observed that this kind of tribology can be used in all IC engines irrespective of type, all IC engines. It can be used in all turbo machineries, for all kind of gears, all kind of cam follower mechanisms, all kind of bearings including magnetic bearings, all kind of seals. So, this kind of knowledge can be utilized for so many components, because I have not seen any machine without any bearing or which does not have any support system. Almost every machine has some support system. That means, every machine requires a tribology. If we are able to implement that, that is going to save a lot of amount, lot of cost which is incurred otherwise. Now, I will take a couple of examples to convey my meaning of the saving related to the nation. Let us take an example of a hard disk drive. We know the hard disk drive is based on a magnetic read and write. Data are picked up or written on the disk using the magnetic medium, and in one hard disk there may be a number of actuators, number of plates. Higher and higher capacity is always demanded. Earlier the maybe say we required a memory in KBs, then in MBs, now in GBs, and now we are talking the terabytes. The capacity of the hard disk is continuously increasing. What is the reason behind that? If I go in detail, I find that all rotary actuator and hard disk, they act as a air bearing. They make air bearing. So, this is blue color is I am assuming that the developed surface is a magnetic disk, and this is a read and write head. When magnetic head is available here, if gap between head and disk is very narrow, very low value, then there is a possibility of boundary lubrication, there is a possibility of surface roughness of magnetic disk may hurt head and damage the head. There is a possibility. However, if we design this properly, then that possibility can be reduced. What is the advantage of reducing the gap between this magnetic head and a magnetic medium? Can be elaborated through this mechanism. You see, if the distance between head and the disk is lower, then data loss or signal to noise ratio will be very high. If the head is very close to this, data can be directly picked up. If this disk, this head is slightly away, then there is a possibility of external or other data getting captured by the head. So, signal to noise ratio will reduce. That will help me in other way also. If I am able to reduce the gap between these concentric circles, right, or the radius of the one concentric circle is slightly lower or slightly more than other circles, that will be preferable compared to distance between these circles if is very high. You say that if I am taking a radius of 1 mm, a radius of 1.01, maybe say 10 micron difference, then that will be preferable compared to 1.1 mm radius. If there is a shrinkage or there is a very narrow domain available, the signal to noise ratio will improve, as well as is going to save a disk space. In the same size disk, I can store more number of data. So, that is a demand. We want to enhance storage capacity without increasing the space, and that is achievable due to tribology. Now, the surfaces have been generated in such a manner, lubricant layer have been generated made in such a manner, then that there is no loss of the data, and it can be read and write can be repeated a number of times. However, due to the unavailability of the good lubricants, it was very difficult to achieve zero wear or negligible wear of the magnetic disk, but now that is achievable, that is possible. Now, we are talking about this height of roughly 25 nanometer. 25 nanometer is very low value. Our ordinary hair thickness comes roughly 60 to 70 micron, and what we are talking 1000 lesser than that. That means, if I do a parallel cutting of our hair, when I can divide one hair in 1000 or more number of pieces, we are talking about that distance. That is achievable because of the tribology. Let us take another example. What we are talking about cylinders or IC engine cylinders. We know piston is generally supported on the piston ring, and it reciprocates in a cylinder head, and lubricant layer is provided over the piston rings, so that it can freely reciprocate in a piston. But it has been estimated this is one of the major source of friction in IC engine. If I along with that, if I count other sources, is something like valve mechanism. We know very well valves are used in IC engine to open the port for the fuel and air, and close the port for compression and expansion stroke, and finally open the cylinder for expelling out the exhaust gases. So, those valves get very high temperature and they have to reciprocate in a cylinder. Along with that, there are number of bearings in IC engine. If I try to control all this, if I try to utilize good tribology or good tribological knowledge on those IC engine components, there is a possibility of reduction in friction by 15%. 15% has been generally targeted. People have quoted that even they have achieved around 20% saving in friction. Their mechanical efficiency has reached to 95%. An older time the mechanical efficiency was maybe say 60%, then 70%, and maybe say around 3-4 years back it was 85%. Now people have achieved in the 95%. So, great saving due to tribological knowledge is possible. Now, there is another change in technology to avoid or to reduce the tribology knowledge. In older time, this kind of crank, this kind of the valve mechanism was used. There was a cam, push rod, rocker arm, and the rocker shaft, and this signal was amplified to push the piston, push the valve in valve guide. So, we can find out there are a number of tribo pairs, say valve and push rod, there will be some friction, there is a mechanical contact, there is a load applied and there is a relative speed. Similarly, this is the contact pair, push rod and rocker arm and shaft, rocker arm and valve and valve guide. So, there are too many tribo pairs in that, and almost every tribo pair causes some friction losses. That was replaced with the overhead cam technology, where now there is a cam, there is a follower and directly valve. So, all intermediate links have been removed. We know very well, if we remove intermediate link, one is the reliability is going to improve, or reliability of system will be higher. In addition to that, there are a number of tribo pairs which have been eliminated. So, friction loss will be reduced. However, there was only one problem, how to use or how to carry lubricant from crankcase to the camshaft. Now, that has also been resolved. They are able to provide good lubrication or the inverted head condition also, we say that overhead condition also. So, if we implement all this condition, if we implement all this mechanism, there is a huge saving, and a rough estimation says that number of vehicles in the world are more than 700 millions. If I count power range of all the vehicles, I can find out average value will be roughly 30 HP by one motor vehicle, which is on lower side, which is more on conservative side. We are doing a rough estimation, and in worst to worst case, if I assume we are able to save 2% of that energy using tribological knowledge, what we are going to achieve is something like a 420 million HP. That is a huge saving. That means, even the delta improvement on a tribological level is going to help us drastically. So, we should implement, we should learn tribology, we should learn how to apply this tribology in couple of applications. Once we learn that application, how to implement for a couple of applications, we can enhance, we can say enlarge our domain for other applications. The tribology or biotribology is one of the coming up area, and people have worked, they have really designed good prosthetic joints based on tribological knowledge, and they are able to achieve joint efficiency as well as a life up to 20 years. Let us take another example. This bearing example is related to the roller bearing, as a multi-row roller bearing, and it failed due to misalignment, due to wrong mounting, or due to wrong impression of the mounting. Maybe the person who mounted, he was not knowledgeable how to mount it, and in hurry up or the faster work, he mounted this bearing, and this bearing failed within 100 hours. There were two bearings, and one bearing failed in 100 hours, other bearing failed in 300 hours, while estimated life of this bearing was roughly 40,000 hours. So, where is the percentage? 100 hours versus 40,000 hours. 40,000 is very huge amount, when almost 4 years, 5 years duration, while this turn out to be less than 1 month. Now, this kind of bearings are very common. These bearings are common in the steel industry, and we know almost every industry uses a bearing. So, I am just taking only this one example, and when we estimate it, all iron and steel industry, they devote or maybe they keep some money for bearing replacement, bearing purchase, kept in inventory. Whenever there is a bearing failure, they just simply replace without really going through, without diagnosing properly. So, they keep generally 3 to 5 millions for maintenance and replacement of the bearings. That is a huge amount. And roughly in India, we have 10 plus this kind of industry, and I am targeting, if I am thinking that at least 10 industries, I am leaving all other apart, these industries are able to save this much money, that will be very helpful to us. And you say that worst to worst, if I am able to save 10% of the bearing life. As per my understanding, bearings are mostly failed because of the mounting, because of the maintenance problem. If that can be avoided, or I am just saying the rough estimation 10% can be avoided, let it keep a 90% same. Even in that case, we are going to save roughly 3 to 5 millions per year, just based on 10 iron and steel industry. If I am counting all other, if I start counting other bearing industries or other industry where the bearings are used, naturally saving will be huge. In short, I want to conclude with this slide. It says that rough estimation say we can save energy, we can save material, and if I talk in rupees, I talk in monetary point of view, we say that we can save almost 1 to 1.5% of GNP. Our GNP, Indian GNP was a $3.4 trillion. So, what we are talking about, roughly the 1500 million rupees can be saved by implementing right tribological knowledge. However, there is always a problem. People say not all efforts will be always successful. So, I agree with that. We said maybe assuming only 50% efforts are success and 50% efforts are not successful. We are wasting half of money in just putting efforts. We are not getting returns, but only half money which we put, that we are getting returns. So, even in that case, saving will be huge. Is a significant amount of the saving we are going to achieve if we implement tribological knowledge. Thank you for your attention, and we will be covering friction topic in our next lecture.